We saw in a previous lecture how to use these matrices, the translation matrix. We were translating by AB, and this rotation matrix, where we're rotating around a point x1, y1 counterclockwise by an angle of phi, and how these matrices can be used for translations and rotations of a point in a plane. So I want to give an example which illustrates this. And this is from a past quiz. And I want to give the information you need in the quiz or test, namely the rotation and translation matrix. So in this problem, f is a function which rotates about the point A by an angle of pi halves. Again, all rotations are counterclockwise. And then it rotates after that, the result of that, about a point B by the angle of pi. So f can be thought of in this way as a rotation about A by pi halves, followed by a rotation about B by pi. So there are two parts of this problem. One is to calculate what happens to f when we look at the point 3, 0. So we want to take 3, 0, rotate it about A, which is the point 1, 3, by an angle of pi halves, again counterclockwise. And then we want to take the result of that and rotate it about B, which is minus 1, 1, by an angle of pi. Part B, we want to find a point x naught y naught such that f of x naught y naught is x naught y naught. So it's fixed by these rotations. So we start out with x naught y naught. After we do both these rotations, we're back at x naught y naught. So let's look at part A first. This, to remind you, is a rotation matrix. And since we have a couple rotations here, the plan would be to go ahead and substitute the information we have, the angle for phi in this rotation matrix, and the A and B, the coordinates of A and B. Each one separately. For A, we get a rotation matrix using the coordinates of A, and for B, we get a different rotation matrix using the coordinates of B. And of course, the angles are different there too. But before I do that, I'm going to go ahead and do this problem a different way. You certainly want to be able to use the matrices the way we're talking about, but it's easier maybe to do what I'm going to do first here. The difficulty is if I gave you this information and asked for the values at a few different points, then it's going to be easier to do the matrices approach. If I also want you to find this x naught y naught, it's also easier if you use the matrices. So we will have to use the matrices, or we'll use the matrices to do this problem, but let's first look at how we could do part A in a different way. Keep in mind that what we're trying to do then is to figure out what happens to this point again after a rotation about this point by pi halves, followed then by a rotation about this point by pi. So what I'm going to do is just draw a picture and see what happens in the picture. So I have 2 points in these rotations, the 1, 3 and the minus 1, 1. So 1, 3 is here, and then the minus 1, 1 will be right there. And I want to rotate about these points, and I need this point also 3, 0. So 3, 0 is going to be right there. So let's go ahead and draw that in also. And then I want to figure out what happens first when I rotate about the point 1, 3 by pi halves. And keep in mind it's going counterclockwise, so we're going to go this way. And we want to figure out where that point's going to be. So it might be a little bit tricky, I don't know, but you go down 3 and over 2 this way. So what you should try is go over 3 and up 2, and that's going to be perpendicular. So what I want to do is to visualize this. We're going to rotate again this green point about this blue point here, and what you're going to get is that. So that's what happens with the first rotation. That takes care of this rotation. Now we want to take that result and see what happens when we rotate about minus 1, 1 by pi. So this is minus 1, 1, and we want to take this point where it's at right now and rotate it about this point by pi. Now notice a rotation by pi about this point, it doesn't make any difference if you go counterclockwise or clockwise, you're going to end up in the same spot. But we'll go counterclockwise, but it's going to give us the same result no matter which way we do, and we want to do counterclockwise in general. So that takes me to this point. So what I need to do is go in the opposite direction as I did here. Here I went 1, 2, 3, 4, 5, and up 1, 2, 3, 4. So I should go down 1, 2, 3, 4, and over 5 to get to this point. So this gives me the rotation about pi by this. And that point, if we just look at it, we're going over 6 here and down 3. So that's minus 6 minus 3. So the final result after we do both rotations, starting at 3, 0, we end up at minus 6 minus 3. So for part A, the answer is minus 6 minus 3. Now we want to do part A a different way. The way that you're normally going to want to do this is with matrices, and let's see how that works. So again, this problem only involves rotations. If there was a translation here, we would have to use a translation matrix as well, but we're just going to use this rotation matrix. So I want to view these two rotations next to each other as a product of two matrices looking like this. So I take these two rotations and I go ahead and figure out what the two matrices are corresponding to it. So I went ahead and replaced these angles with pi halves here. And with the pi here, I replaced these angles with pi. And then we have 1, 3. So in the rotation matrix, for the pi halves, I'm going to have a 1 here and a 3, a minus 1 and a 3 there. So I have 1 times this, 3 here, a minus 1, so minus, and a plus 3 here. And so this is the same thing as this, with phi equal to pi halves, x1 equal to 1, and y1 equal to 3. So this one, again, I've already replaced the angle with pi. We talked about that. Now the x1 becomes minus 1 here, and the y1 is 1. So I'm going to have a minus plus 1, and this can become plus 1 because it's minus a negative 1, and this will be 1. So we have a minus plus 1, again a plus 1, and a plus 1. So this is the matrix we have up here, again, with phi replaced with pi, and x1 and y1 replaced with minus 1, 1. So we have these two matrices. The product of these two matrices should represent then what's going on with this product. Let me first simplify what these matrices are. Cosine of pi is negative 1, sine is 0. So that's where this is coming from. And of course, this as well. So the zeros are down there, where the ones are always there. And then we have the minus 2 and 2 on this matrix. And where is that coming from? Well, I'm just plugging it into what we have here. So we have 1 minus a negative 1, which gives me a 2. So that makes it minus 2. And this is 0. So that's giving me this minus 2. Here we have 0. 1 minus a negative 1 gives me 2. This is always 1. So if you can't see it, there's a 1 down there. This matrix, pi halves, cosine of pi halves is 0. The sign is 1, so we have a minus 1, 1 there. Minus 1, 1, and zeros. And then on this part, this is 0 again. This is 1, so we have 1 plus 3, which is the 4. We have a minus 1 plus 3, which is 2. And again, this is always 1 down here. So that's what the two matrices look like. And now we want to go ahead and do a a product of these two matrices, and let's look at that. So I claim it's this, and maybe, so this is out of the way, I'll go ahead and put it up here to see where this came from. If I want to know an entry over here, this is a 3 by 3 and this is a 3 by 3. You look at the first three here and the last three there, you get a 3 by 3. If I want to know what the product of these two matrices are, what you do is to go ahead and take this row dotted with this row to get the first entry. So I have minus 1, 0, plus 0 times 1, plus minus 2 times 0, and that just gives me 0. But in general, if I want to know a particular element over here, let's say this one, this is in the second row and third column of this matrix. So I look at the second row and third column here. So the second row of the first matrix, the third column of the second, to give me the second row, third column element over here. And I just take the dot product of these two. So 0 times 4, which is 0, minus 1 times 2 gives me a minus 2 that I add to that, and then 2 times 1 is a plus 2 that I add to that. So just 0 minus 2 plus 2, which is 0. Let's take this example. This is in the second row and first column, so I'm going to take the second row and first column and take the dot product. We have 0 times 0 plus negative 1 times 1 plus 2 times 0. So that's just negative 1, and that's where this negative 1 comes from. So I go ahead and do all those computations, and this is the matrix I get. So the product of these two rotations is just this matrix. Now, if I want to know what happens to a point 3, 0, then I go ahead and put an extra 1 here and put 3, 0, 1. And I just take the product we just found, this matrix, and multiply it by 3, 0, 1. So that's this row dotted with this, and then this row dotted with this, and then this row dotted with this. So we get 0 plus 0 minus 6 is negative 6, minus 3, and then 0 and 0 give me minus 3, and then 0, 0, and 1 give me 1. You'll always have 1 there, so you don't really need to check that. But this is telling me then that f of 3, 0 is going to minus 6, minus 3. So the end result would be minus 6, minus 3, like we had before for what f of 3, 0 is. Now, the nice thing about this approach, again, is if I gave you a lot of points, not just ask for f of 3, 0, but ask for f of 2, 5, or whatever, all you have to do is change this to 2 and 5. This matrix stays the same. It's still the product of the two rotations. So you're just going to take this matrix, put 2, 5, 1 here, and figure out where it goes. So you can do a lot of different points at the same time using just this one matrix. So let me go back. This was the problem. We just answered this question. There is another question here, and that is to find the point x naught, y naught that's fixed by these rotations, where you start out with x naught, y naught, and you end up back in the same place. So again, the matrix form of the problem is the easiest thing to do. So let me put this up here. We want to go ahead and look at where we were before. We had all this work done, and we don't need to repeat that work. We got the product of the two rotations as this matrix, and that's what we're going to use for the function f as being the product of those two matrices. So we want to do something similar to what I did here, but I want to start out with the point x naught, y naught, and I want to make sure I end up with the point x naught, y naught. So I start out with x naught, y naught, and I want to take, again, the product of those two rotations and multiply it by x naught, y naught, 1. So what we're actually going to get then is 0 plus y naught minus 6. So we get y naught minus 6. Here we're going to get minus x naught, 0, and 0. So that's minus x naught, and then again, you'll just get 1. So that doesn't look like x naught, y naught, 1, and that's because, well, it's not going to be true all the time. It's not going to be true that for any x naught, y naught, 1, I end up with x naught, y naught, 1. I have to find the one where it's true. So in other words, I'm trying to find out when does this result of these two rotations end up being this. So I need to check when is this equal to x naught, y naught, 1. So this is what I'm trying to check. Well, this gives me two equations, x naught equals y naught minus 6, which I can rewrite as x naught minus y naught equals negative 6, just by bringing the y naught over. And then the x minus x naught has to equal y naught, which I can rewrite as x naught plus y naught equals 0. Well, I want to solve for x naught and y naught in these two equations to make these two equal. The easiest thing it looks like to me is just to add these two equations. The y naught will disappear when I add the two equations. I add the two left-hand sides. I'm just going to get a 2x naught. I add the two right-hand sides. I'm going to get minus 6. So 2x naught equals minus 6, or x naught equals minus 3. And once you have x naught is minus 3, you can look here. Y naught has to be 3. Or you can look here and add x naught to both sides, and you'll get this is minus 3, and so this is minus y naught, and y naught is again 3. So either way, you're going to get y naught equals 3. So this must be what x naught and y naught are in order for this to equal this. And once that happens, we see that the double rotations of x naught, y naught are going to end up being x naught, y naught. So the answer to part B is the point minus 3, 3. So that is the point that stays fixed under the double